Welcome to the Copper Spice YouTube channel, and thanks for joining us. In this video, we will talk about how the C++ standard describes the differences between a forward declaration and a class definition. Class completion. As programmers, we frequently add new classes to our code. But are we using the terms for declaring and defining a class accurately? Have you thought about what happens when you forward declare a class and what is allowed with a declaration? Are you taking declarations for granted, or have you considered why this works? The idea of class completion is defined in the C++ standard. There are other sections which define declarations and definitions, but you have to pull together all of these to fully understand classes. Knowing exactly when a class is complete or considered complete allows you to design your code correctly. After we discuss the terminology, we will provide some examples to help illustrate these principles.
Let's start by doing a quick review of the definition of a data type. This is important since a class is the most obvious way to create a new data type. The computer science definition of a data type consists of two distinct parts. There is the set of possible values the type can contain, and then we have the operations which can be used with the given set of values. For a data type like an integer, the set of possible values are numbers like 0, 8, or 17. The operations might be things like adding two values, copying the value to a different variable, or comparing two integer values. When we declare a class, we are defining a new data type. When the class is in scope, we can use it just like any other data type. Since a type contains values, the definition of a class must indicate the set of possible values, which is the combination of all values the data members can contain. The methods available in the class define the operations which are supported. A forward declaration for a class or struct is used to set up the name of a new data type. It does not provide the rules for the definition of the new type. In this talk, when we refer to a class data type, all of the information also applies to a struct. You may have code which acts like a forward declaration of a function, but this does not create a new data type. It is possible to forward declare an enum. However, the rules of class completion do not apply to enum types. The term forward declaration is pretty clear. The purpose is to declare something. Since there is no definition, there is not enough information for the compiler to determine the list of possible values or the operations which will be supported. The new data type corresponding to the class name is called an incomplete type, and the ways it can be used are extremely limited. For example, you cannot construct or instantiate an object of this type, since there is no guarantee the class is constructible. All you can do are generic things, which are not connected to the possible values or operations. Here is an example which contains a forward declaration of the class Ginger. Since there is no definition of Ginger, it is an incomplete data type. If we look at the member declarations in class Widget, located on line 1 and line 2, these are both valid and the code will compile. Few will be surprised that line 1 is okay. Most programmers would say the reason why is that the compiler does not need to know the size of a Ginger type in order to allow the declaration of a pointer to that type. However, this is not how the standard defines the situation. The technical reason why this code is valid is that a pointer to any data type is valid. Keep in mind, the forward declaration says there is a type with this name, even though we have no idea what it means. The fact line 2 compiles may be surprising. The standard is clear about when type T must be complete and therefore usable in a declaration. Static data member declarations, which are not a pointer or reference, do not require that the class be complete. The definition of object 3 is invalid, and this code will not compile, since declaring a non-static class data member requires a complete class. There are multiple reasons why this declaration is not valid, including not knowing the size of the object or what constructors might exist. The standard does not contain those reasons and simply says it is not valid. The last two lines are a bit interesting, and we had these backwards at first. Receiving Ginger by value requires a class to be complete, but only for a method definition. Line 4 compiles, since it is a method declaration, where it is permissible to receive an incomplete type by value. The very last line does not compile, since we added an implementation, which makes this a method definition. This line would require the receive parameter to be a complete type for it to compile.
These are the terms used in the C++ standard to define class completeness. When a class is incomplete, a definition either does not exist yet, or the class definition is in progress. Inside the definition, as the class is being defined, we have a partial definition, but the class is still incomplete. What can be confusing is at some places in the class definition, the class is considered complete. These regions are referred to as complete class context. We have some examples which will help to illustrate this idea. Once a class is complete, all of its data members and methods are defined. The values and operations are completely known, and the entire class can be used. It is probably not surprising to learn a class is complete after the closing curly brace of the definition. But are there other places in the definition that a class might be complete? Well, the standard defines 4 other locations within the body of the class definition, which have complete class context. The first of these occurs between the curly braces of the implementation of a class method. This is why it is legal to use members inside a method of a class definition. When you are in a complete class context, everything else in the class is visible, no matter where the code resides in the definition. The class is also in a complete class context after the equal sign, which defines a default argument for a method parameter, and inside the parentheses of a no-except condition. The fourth location is after the equal sign of a non-static data member initializer. Let's take a look at a few examples.
This is code which most developers would say declares a class. Actually, the only declaration is the very first line, which says class Ginger. Immediately after the identifier Ginger, the name has been declared as a data type. From the opening curly to the closing curly is the class definition. This is followed by a semicolon. The purpose of this example is to show where class Ginger is considered to be in a complete class context. We have highlighted these regions in yellow. Line 3 shows a default argument for the parameter count. The default is not specified as a number, but rather the data member x. Since the standard says you are in a complete class context after the equal sign of a default argument, the data member x is visible, and this code compiles. The visibility we are talking about is not related to the access specifier, which happens to be private in this code. The variable x is only visible where the class is in a complete class context. Between the curly braces of the method implementation for F1 we are also in a complete class context. This explains why mData is visible and usable, even though it is declared later in the class definition. On line 7, we are using the data member X to determine if method F2 is allowed to throw an exception. This is another place the class has a complete class context, namely inside of a no-except condition. The last remaining place there can be a complete class context is after the equal sign of a non-static data member. Since the declaration for mData is non-static, we have met the first requirement. The variable x appears after the equal sign, so now we have met condition 2. Since we are in a complete class context, the initialization of mData can view the entire class definition. This is why we can use the value of x to initialize mData. In our last example, we want to show another aspect of a complete class context. In this definition of class Ginger, we are declaring a method named count, which is intended to tally the number of characters in the received string. There are 2 lines of code which call count before its declaration on line 3, and then 2 lines of code which call count after the declaration. The question is, are these calls valid according to the standard? For clarity, the answer would not change if we supplied an implementation for the count method. Looking at line 1, we have a call to count to initialize var1. Remember, the initializer for a static data member is not a complete class context. This means line 1 does not compile, since the declaration for count is not visible, which means the initialization cannot happen. On line 2, the count method is visible after the equal sign, because we are initializing a non-static data member. So this line compiles because var2 can be initialized. Once we reach the declaration for the count method on line 3, the situation changes slightly. Line 5 declares another static data member just like line 1. Even though we are not in a complete class context after the equal sign, the count method is now visible since it is declared above line 5. But there is a new twist. var5 is a static data member, so the count method needs to return a constant expression. Since count is not constexpr, line 5 does not compile.
We have added lines 4 and 6 to this example to show how to initialize a static const data member. Line 4 returns a constant expression, which is then used to initialize line 6. Both of these lines compile. Although line 7 is in a complete class context after the equal sign, the initialization of var7 is located after the declaration of count, so this line compiles for both reasons. Here is the wild part we discovered about line 5. We actually expected this line of code to compile, since the count method is visible. Getting a compile error saying var5 needed to be initialized with a constant expression was a bit unexpected, but okay, we can add that. So we tried to add a constexpr to the declaration for the count method on line 3. But that constexpr is ignored by the compiler, since class Ginger is incomplete and we are not in a complete class context. As one other experiment, we changed the initialization of var5 to call a different constexpr method in another class, and then line 5 did compile, which was not a huge surprise. So the rules for class completeness are precise, and the order of declarations in a class definition impact what is allowed and what will not compile. To ensure you understand this part of the standard, we encourage you to experiment with this example.
For more information about the CopperSpice project, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. If you have any questions or feedback, feel free to leave a comment on this video or send us email.
Please make sure you subscribe to our YouTube channel and come back in a few weeks for our next video.